Let's take a look at a more interesting problem now, where we have different properties given to us. Let's consider an H2O blob in the gaseous phase with a pressure is not given to us. Instead, what we're told is that the temperature is 965 degrees centigrade and that the specific volume is 0.06510 meters cubed per kilogram. So in this case, we have two independent intensive thermodynamic properties, and they can give us the third one. And we want to find the pressure. This isn't a very difficult problem if we have a closed form equation of state, but what about when our governing equation turns out to be a table? So we know that for water, we're typically going to be using tabular equation state, and for gassy water we use table A6. So if we were to take a look at table A6, and this is table A6 shown to you on the screen for superheated water, what we can see is that we're not given a pressure to start looking at. Instead, what we've got to do is start looking at something we do know, and that would be a temperature. The temperature we're given is also not in the table, but we know that 965 degrees centigrade is going to lie in between 1000 and 900. So if we look across here, we see, okay, the specific volume would be between 0.13 and 0.14 for a pressure of 4 megapascals. If I increase the pressure, that goes down between 0.11 and 0.103. Well, I want 0.06. So let's continue reading over between 900 and 1000. Here we're at 0.08. Here we're at 0.07. And then finally here we hit a number. Okay, we've got 0.067 and 0.073. So the number that would be interpolated between these two values would be greater than our number of 0.065. We're getting closer though. If we go down to the next isobar data of 9 megapascals, we have 0.05 and 0.064. Well, this number maxes out at 0.064, so the number we would interpolate here would be, it would have to be less than our number of 0.0651, which we're given. So let's make a table to make this very clear. So we would have pressure data at 8 megapascals, and then also pressure data at 9 megapascals, and we don't know the pressure that we're at. It's an unknown. What we do have are specific volumes given to us, and we've got some temperatures. Our temperatures, though, are bounding our desired temperature of 965 degrees centigrade. So at 900, we can see that we, as we saw in a second ago, we have 0.067 and some trailing figures. And at 1000, we have 0.073. Then at 9 megapascals, at 900, we see we have 0.059 and 0.064. And ultimately, we know that at 965 degrees centigrade, our specific volume should read 0.06510. So if we were to interpolate between these two numbers, we would get a number in between those two. They would show up right here, and it would have to be greater than 0.065, as we've already determined, since it would have to be, the smallest it could be, it would be 0.067. And then if we were to do the same thing and interpolate between these two values, we would get a number that has to be bigger than 0.064. So in other words, we are right in between. Right? We can now interpolate in this direction once we have those two values. So let's go ahead and use MATLAB to compute those values. And we'll go ahead and we'll use our same file that we've already started a second ago. Let's go ahead and first find the specific volume at 8 megapascals for our given value of 965 degrees centigrade. So in that case, we're going to use interp 1, and our x value in this case is the temperature, and our y value would be the volume. So we're going to be between 900 and 1,000, and we're going to have our values of volume there are going to be cut and paste directly out of our code here, so out of our singles book we have available to us, the appendices. And what we're interested in is this at 965 degrees centigrade. Great. Let's do the same thing, but now at 9 megapascals. And we're going to cut and paste these values just as easily. Let's do it quick. And we're once again interested at 965 degrees centigrade, what the value is. And then lastly, what we'll do is interpolate between these two values to get the value right here. Let's just run this code as it is at the moment. So the number that goes right here is going to be 0.07098, and the number that goes right here, 0.063044. And now we're going to interpolate in between these two to get the pressure. So the pressure is the unknown in this situation. Going back to MATLAB, we're going to have our ultimate pressure that we're looking for in this problem is going to be interp 1. Now we're going to interpolate between volumes. And our known volumes now are V8 and V9. And the pressures at V8, well, that would be 8 megapascals. And at 9 megapascals, we know it's V9. And we're interested in that pressure when the volume is 0.0651. So let's run this code one last time. And we have just found that our pressure, 0.0741 megapascals, is determined.